Okay, thank you so much. Thank you to the organizers for the opportunity to speak, this lovely conference, all that. So this is some joint work with Christian Gates, Oliver Chenik, Stefan Fauner, and Jessica Stryker. It's kind of a follow-up of the talk that Jessica gave. And then the stuff at the end will also be with Hai-Han Wu. Okay, so let's get to it. I'm actually going to go pretty quickly through the first half or so because Jessica ostensibly already did it. So an hourglass plabic graph is a planar bipartite graph embedded in a disk. Edge weights 1 through r, which sum to r around internal vertices. Boundary vertices have degree 1. And here, if we have an edge weight of like 3, we draw it using this funny half twist, which we call an hourglass. Here is an example of an r equals 10 hourglass plabic graph. Around each internal vertex, you'll count 10 strands. So why does one care about these guys? My motivation tends to come from morphisms in quantum groups. So in particular, we can encode a morphism in a tensor product of, say, fundamental representations, really the invariants you might be interested in. Just as a quick example, this is in the q equals 1 case, this encodes the determinant. And if you're curious, the funny hourglass onion things end up turning into exterior powers. We'll talk about briefly why we want to do these funny hourglasses. Why might you do this at all with this web story? A lot of times you're interested in sort of effective calculations, maybe link invariance, but I won't talk about any of that today. I will instead talk about how our framework connects 3 well-loved classes of combinatorial examples, namely alternating sign matrices, plane partitions, the Tamari lattice, and then I'll kind of go into some more detail on the ASMs and PPs and some geometry that Jessica did not go through. So, quick crash course. Postnikov introduced plabic graphs, which are similar to hourglass plabic graphs. He doesn't have hourglass edges. The key thing about plabic graphs is that they have trip permutations. As Pasha was saying, we take a left at white, we take a right at black, and so this, for instance, is a trip permutation there. We can compute, this is the cycle notation of the trip permutation of this plabic graph. So Postnikov also gave a lovely characterization of when plabic graphs are reduced. There's a bunch of adjectives, qualifiers that you need. I'm going to skip that for this talk. The key things are sort of, you can phrase them in terms of trip permutations. They're 3 forbidden configurations. So no round trips, for instance. No trip where you go just strictly inside without reaching the boundary. No self-intersections. And then also no bad double crossings. That's kind of an interesting one.
What was the theorem part?
The what?
You said theorem definition. Where is the theorem part of that definition?
Oh, sure. Okay. So there's another definition of reduced, more like what Pasha was saying. We have these moves that you can use to reduce a thing. That's sort of really the official definition of reduced, and then it's a theorem that it's characterized in terms of what trips can't do. So it depends on your perspective. Thank you for the question. Okay, so Postnikov had given a lovely characterization, basically classifying plabic graphs, you might say, by their trips. And this is if and only if they're related by certain moves. The most important by far being a square move. Here I've drawn the little trip permutation. And when you do the square move, the trip kind of reroutes in the interior, but from the exterior it looks the same. So the trip permutation is preserved. And then the other 2 are less important. Okay, so the 5 authors, the second S being me, listed at the front, we introduced this larger context of our hourglass plabic graphs. And the key difference between them and regular plabic graphs is we track multiple trip permutations. So trip 1 through trip r minus 1, where trip I takes the ith left or the ith right. So here I've drawn trip 1, 2, and 3 through a hexagon. This is in the r equals 4 case.
Sorry, what's ith left and ith right?
Sure. So let's look at the red. So that's trip 1. It takes the first left, so the most left, then the first right. And then through this little onion, so this is sort of the key bit of why we have these onions at all. We need to kind of route it around like that. So we need the 5 to be connected to the 1 for things to sort of work out the way we want them to.
So it's trivalent, that's why, okay.
Yeah. So only for the purpose of computing trips do you care about tracking onions, hourglasses.
Only the parity of the onion plays a role?
I'm sorry?
Only the parity of the...
Only the parity? We care about the whole tuple of permutations. So one cute thing about this setup is because we're R-valent on interior vertices, the ith left is the same as the R minus ith right. So this leads to a nice symmetry, and really only half the trip permutations are actually interesting. So we characterize, so we have a notion of fully reduced, actually a couple notions, but one of them can be phrased similarly to how I phrased Postnikov's, like, trips don't do bad things definition. There is an interesting interaction. Here we require we need to forbid interactions between, like, trip 1 and trip 2 strands, rather than just trip 1 and trip 1. But in any case, we were able to do it, and the key is that there are two different types of moves. This is from Jessica's slides, / the paper. There's the benzene move, and then there's the square moves. So the square moves, they're very reminiscent of the regular plabic moves, but the benzene is sort of fundamentally new to the hourglass SL4 case, so the 4 hourglass case. Here I've noted the top and bottom for later use. So you can phrase the main theorem, at least combinatorially, as giving a bijection between 4-row standard tableau and move equivalence classes of such appropriately reduced 4 hourglass plabic graphs. And moreover, there's a way that you can compute sort of what trip permutations you want to have, purely tableau theoretically, called the promotion permutations that Jessica had introduced, which I will not define at all in this talk. So here's just a pictorial example. If we have this particular tableau, it turns out you run the bijection and you get the equivalence class of these two fully reduced hourglass plabic graphs, and they are in fact related by precisely that benzene move from this slide. Okay, so now we're up to the first thing I wanted to say. So I had said that there were these 3 lattices that sort of fit inside of our framework. And the takeaway that I want to leave you with is that our framework includes at least these 3 sort of beautiful, well-studied, well-loved lattices as extreme examples. But it also kind of includes connective tissue between them, a highly structured connective tissue. So here's the plain partition version. The move equivalence class associated to here, I have to use an oscillating tableau, and I'm writing it as a lattice word, really a highest weight word. The details don't matter. You can interpret this as a tableau-like object. Jessica had written out fluctuating tableau. Anyway, the move equivalence class associated to that guy is in natural bijection with plain partitions. And let's just do the picture. Again, Jessica's slides. So here, that ends up being the tableau. And if you look, this is one particular element of the move equivalence class. Applying benzene moves can be thought of as adding or removing boxes. So just 2 brief features of this that I wanted to emphasize. Trip 1 actually doesn't really see hourglasses. You could have or remove hourglasses, and it turns out it will have the same behavior. It won't get rerouted around faces. However, trip 2 does see hourglasses. I had shown you this orange strand here. It kind of routes that way around the hexagon. If you flip the configuration, it will be rerouted on the other side. So in some sense, the trip 2 is kind of seeing local but not global differences, and trip 1 doesn't see anything.
The trips will see it, but the permutation has to be the same.
Correct, yes. The overall global permutation sending boundary to boundary will be the same. Mm-hmm.
So for plain partitions, the column of your fluctuating tableau is always empty?
Let's see. So yeah, I guess I didn't use 3s. So yeah, from this parametrization. Yes. Uh-huh.
Sorry. So benzene moves don't change trip permutations, right?
Correct.
It's then trip 2.
They change the trip.
They change the trip. Okay.
Yeah. The sort of physical trip reroutes and takes different roads, but it ends at the same place.
Should be basically the same as the non-intersecting lattice path version of the permutation.
Oh yeah. You can interpret it in that way somehow. Yeah.
Yeah,
it's been a few months.
That's
since
what
I've
my question should have been.
done it. Sure. Yeah, anything else? Okay, so I said as a set. Oh, yes, sorry.
Yeah.
Lauren.
Can you tell me how I should look at the figure on the left and see that this is the right tableau to give rise to these, or I don't know, I'm not.
There's an
quite
algorithm. It involves like 100 or so rules. So there is a way, yes. In some sense, yes, but there's not probably a satisfying answer. At least not that I know of. Okay, and so you can get the poset structure by saying that you can kind of order these benzene moves. So say that's just going straight up. That would be the poset direction. Okay, so that's one of them. Next, alternating sign matrices. So it turns out, move equivalence class associated tableau with lists, nice super standard lattice word. This is just 1, 2, 3, 4, 5 up in the first row, etc., filling row by row. These guys are in bijection with n by n alternating sign matrices. Again, picture says 1,000 words. So here's that super standard tableau. Turns out that turns into the move equivalence class of this. Here I've drawn it rather than in a circle. I've kind of squared off the boundary. It doesn't matter. You can interpret this thing as an ASM by sort of squishing together. We call these transmitting vertices into zeros. White vertices, white sinks or sources become ones, black become negative ones. Turns out bijection. Let's see, interestingly, so here, trip 2 doesn't see any difference about square moves. It doesn't get rerouted around the face, but trip 1 does get rerouted. So it's kind of the opposite of what's happening. Another thing that I guess maybe I should have said before was in the plane partition case, we have benzene moves. It turns out there are never any square moves applicable. Here it's the opposite. We have square moves. It turns out there's never benzene moves applicable. So they're kind of dual here.
Sorry, could you go back to the previous slide? I mean, when you say move equivalence class is associated with, so what is in bijection with, so for each alternating sign matrix?
There is a web where the trip permutations of the web are the same as the promotion permutations of that lattice word.
So the equivalence classes of, the orbits of the promotion permutation, are they?
Fibers, I guess I would say.
So there are many possible trip permutations.
My question, yeah.
So if you do square moves on this, the trip permutations will all be the same. And they'll all be the same as the promotion permutation of this lattice word, whatever that is. In particular, for instance, it turns out that the second promotion permutation of this guy sends 1 to 1, 2, 3, 4, 5, 6, 7, 8, 9. It just kind of goes straight across. And if you trace through the trip 2, no matter what, even if you apply square moves or whatever, it'll still go straight across. Anything else? Yes?
These tableau on the left, they have some parity condition?
No, just rectangular.
Okay, so it's not that the labeling should match, the parity of the labeling doesn't match the cell or anything?
Yeah, no, just the number of these. The number of boundary vertices needs to be the same as the number of cells in the standard case, for instance. That's about all. Yep. Okay. And again, there's a way that you can get the poset structure. It's slightly like non-canonical, but it's like combinatorially canonical.
So sorry, so trip 1 is going to be which non-intersecting paths now?
Let's see. I don't think I'd be able to do it off the top of my head. Sorry. I encourage you to work through what trip 1 is in this example. It is fairly straightforward to work out. Yeah, it's kind of fun. Okay, so I've given you 2. Third one, Tamari lattice. It can be thought of as the set of triangulations of an argon, and there's a way to order it so that it has the structure of a poset and magically a lattice. I also need to mention the general square moves. I'll reference a few, Kautas, Kamnitzer, Morrison, Fraser, Lamb, and Fraser. where this sort of thing has appeared before. Here's a general hourglass plabic graph square move. Here I'm assuming sums of R around each guy, and I've suppressed the onions because I don't care about trips at the moment, but they're there. So Fraser introduced a construction of these, of a web basis indexed by standard tableau of two-column shape. So this, two-row shape, Temperley-Lieb, three-row, Cooperberg 30 years ago, four-row, us a year ago, Fraser, two-column, also recently. And so Fraser's construction actually yields a bijection between two-column tableau and square move equivalence classes of fully reduced hourglass plabic graphs. So we have a notion of fully reduced where you forbid sort of bad trip behavior, and it turns out Fraser's combinatorial construction sort of precisely gives you the image of that construction. So it sort of fits very beautifully into our framework. Also, promotion and trip are the same. I'm going to, in the interest of time, just click quickly through the construction. There's sort of a Catalan bijection, and you kind of squish some things. And then you have some dissection of a polygon, which you in general turn into a triangulation in an arbitrary way. And then you turn that into an unweighted graph, and then you put some edge weights on in a certain way, and out the other side you get actually the example I had put up before of an hourglass plabic graph, in this case for r equals 10. The connection to Tamari is the move equivalence class associated with, again, in this case, actually the superstandard lattice word, but this time with R rows. And so I should emphasize here that this is sort of an SLR phenomenon. Before we were in rank 1, 2, or 3, really mostly 3 for R equals 4, but this is arbitrarily high rank. But anyway, so that move equivalence class is in bijection with the Tamari lattice of triangulations. And so here's just an example recovering the square move, in fact. Don't have time to go through it, but you end up getting either of these two triangulations, and they are indeed related by the square move. So let's see, that's those three things that I mostly wanted to get to. Now the rest is gravy. We'll see how much time I have. I'll mostly just show some pretty pictures. There's a beautiful story, Fontaine, Chemnitzer, Cooperberg, sort of discussing web bases and affine buildings, and ongoing work following a suggestion of Cooperberg with Hai-Han Wu, his student, associates sort of our new SL4 basis stuff with pockets, which I believe is very beautiful. So I don't have time to get through that, I don't think. The affine Grassmannian is a thing. There is a notion of distance on points of the affine Grassmannian, but rather than being like real valued distance, it's dominant weight valued distance. Kind of weird, but it ends up working out nicely. And there are some important distances, the fundamental weights. The fundamental weights correspond to exterior powers of the defining representation. They sort of generate the representation theory through the Karoubi envelope construction, all that stuff. So the affine building is a simplicial complex whose vertices are points in the affine Grassmannian, and simplices are sort of collections of points that are fundamental distance apart. There's an embedding, so let's just switch to the pictures. Here's the SL3 or NSL3 web basis. You can embed the dual graph, it turns out, inside the affine building. You pick some sort of vertices, elements of the affine Grassmannian for each face, and it turns out that they have some distances. You can define a notion of distance, and it works very nicely. So maybe I'll just finish on this slide. So we can construct, sort of in the SL4 case, three-dimensional pockets inside the affine building, where slices of them sort of precisely encode elements of the equivalence class of hourglass plabic graphs up to these move equivalents. And so here, for instance, the square move on the level of plabic graphs turns out to be kind of toggling which side of this diamond you're going on. And here's a few more pockets. I really like this one, pocket of a chained hexagon, if you recall Jessica's talk. This one is a chained pentagon. It's not embeddable in R3. There we go.